Good day. Welcome to the second video on chapter 1.7 cross products. Why are we really doing cross products? Let's start with a question. Let plane P be the set of 3D vectors of the form vector 111 plus t times the vector 234 plus s times the vector 345, where s and t are real numbers. And the question is, so this plane P, which is a flat surface, is the point 10, 17, 18 on point P, or any other point that you would like to know? Is it on point P, on plane P, or not? Now, to answer this question, you've got to ask yourself the following question. Does there exist real numbers s and t that satisfies the following equation? So for it to be in set P, the vector 10, 17, 18 must be of the form 111 plus t times 234 plus s times 345, where s and t are real numbers. So if you simplify the right hand side, it becomes a 3D vector, and the left hand side is a 3D vector. And we know that two 3D vectors are equal if the first components agree, and the second components agree, and the third components agree. So you end up getting three equations and two unknowns to solve, and it's pretty messy, right? If you get a solution, then the point is on the plane. If you don't get a solution, the point is not on the plane. So it's pretty tedious, all right? So this leads then to a following question. How can we find a nicer representation of a plane? And do a nicer representation of a plane exist? And the answer is yes. It is called the Cartesian equation for a plane. But first, let's do a theorem. This is Theorem 1.7.16 in the textbook. Let n be a non-zero 3D algebraic vector, and let R be any 3D algebraic vector. The set X, which is all the 3D vectors, such that n dot x minus r is 0, is a plane in 3D. All right, this is the theorem. So if you have a non-zero vector n and any vector r, then n dot x minus r, so the set of all x's that satisfies this equation, that object is nothing other than a flat surface or a plane in R3. The proof is quite long, but I'm just going to give you a brief overview or an outline of the proof. So from vector n, we construct points P, Q, and R, 3D vectors, not all on the same line. And then what we do is, after we've done that, we define set P to be the set of vectors of the form R plus S, P minus R plus T, Q minus R, where S and T are real numbers. And now, because P minus R and Q minus R are not scalar multiples of one another, another way of saying it, P, Q, and R are not on the same line, it follows that set P is a plane. Now, we do this in a very special way, in a very clever way, so that we can show that set P and set A is identical. Now, remember from set theory, how do you show that two sets are identical? You need to do two things. You need to show that if X is an element of P, then X is an element of A. That's job one. And then job two is you've got to show that if X is an element of A, then X is an element of P. And once you've done that, then you know that set P and set A is the same. Now remember, P from earlier is a plane. And if P and A is the same set, then A must be a plane. And there you go. The details are in the textbook. So if you want more details, please read the textbook. But this is just a brief overview. All right. Now for another important theorem. Theorem 1.7.17. If P, Q, and R are any three distinct points in R3 not lying on the same line, then the following two sets are the same. The set P, R plus S, P minus R plus T, Q minus R, where S and T are real numbers, and the set A is n dot x minus R, where x is any 3D vector, is the same set where n is P minus R cross Q minus R. Oh, my apologies. This should be the other way around. What I want to write down here is x is any 3D vector with the property that n dot x minus R is equal to the 0 vector. All right. So when you write this in set notation, this is what you want, and this is the criteria. So I had the other way swapped around. So here, the criteria is that S and T are real numbers, and then you want all of these vectors. Here we want any vector x with the property that n dot x minus r is 0. Alright? Now, these two sets are the same if vector n is p minus r cross q minus r. Alright, now some remarks on Theorem 1.7.17, that x is therefore an element on plane P if and only if n dot x minus r is equal to 0. Because you will show, if you try it, that set P and set A is the same set, so it is the same plane. Alright, now why this is important to us is that n dot x minus r is equal to 0 is called the Cartesian equation of the plane. So if you simplify it, you will get that it's a single equation and it's called the Cartesian equation of the plane that you are studying. Vector n is very special. It is called the normal of the plane that you're studying, and very important. Emphasize this, n should always be a non-zero vector if you're dealing with a plane. X is equal to r plus s p minus r plus t q minus r, where s and t are real numbers. We said before it's called the vector equation of the plane. Now, the Cartesian equation of the plane and the vector equation of the plane is not unique. Now, a little bit of a geometric meaning. So, if A is a point on the plane and B is a point on the plane, then you can form the line that passes through A and B, or you can form the ray that starts at point A and passes through point B, and then you can form the following ray that passes through point A and passes through point A plus n. So A and B should be different points on the plane. Then we can form the following two rays. So the first ray is A plus T B minus A, where T is greater or equal to 0. So this is the blue ray, ray 1. And then you can form the green ray. So the green ray is the second ray, ray 2, that passes through A and A plus n. So it's of the form A plus Tn, where T is greater or equal to 0. Then for any point B, if you do it in this way, then the ray 1 and ray 2 is perpendicular. So the angle between the rays is pi over 2. So another way of saying this is that if you draw any line in the plane, that it will always be perpendicular to a normal vector. So you just have to appropriately construct another line, and that it will always be normal. Alright? So as you can see, normals are not unique. So all that you need to know is that if n is a normal vector, then alpha times n, where alpha is a non-zero scalar, is also a normal vector. And in this way, you can find all normals. So you just take a normal and you multiply it with a non-zero scalar and you find another norm. Alright, let's do some examples to see this in action. So some examples where we get to use these theorems and the typical questions that you can expect us to ask you. So here we have 3 points in space, P, Q, and R. They are 3 points in space. So the first task is, does a plane exist containing P, Q, and R? So the first question is, does a plane exist that contains P, Q, and R? Alright, so we are going to start off by calculating the following. We're going to calculate P minus R cross Q minus R. So P minus R, so you subtract vector P, you subtract it from vector R, and this becomes first component 0, second component 3, third component minus 2. Then you go Q minus R. So Q minus R, you subtract the first component, which is 1, the second component, which is 2, the last component is minus 1. And then you use this nice little trick, so you write down 0, 3, minus 2, repeat 0, 3. Then you write down 1, 2, minus 1. Repeat the first two components, 1, 2. Delete the first column, and then you have that minus that. And if you do the maths, it becomes 1. Do you agree? Then you do that minus that. If you do this, you get minus 2. And then you do that minus that. And so it becomes 0 minus 3. That becomes minus 3. And this is not the zero vector. So we can say, well, we're in business, all right? Since P minus R cross Q minus R is not the zero vector, thus we have that P minus R is not a scalar multiple of Q minus R. Alright, so this is good news. So therefore we have that a plane exists. Therefore such a plane exists with normal, and then the normal would be n, which is given by P minus R cross Q minus R, which we just worked out is 1 minus 2 minus 3. Alright, and now we can give the equation for the plane. So we can say, so the Cartesian equation is n dot x minus r is equal to 0, where I'm going to use the convention that vector x has components x, y, and z. And now let's fill in. So n is the vector 1, minus 2, minus 3, dotted, brackets are your friends. So this is x, y, and z, minus r is the vector. R is the vector with components. Let me just scroll up to see what it is. 1 minus 1, 1. So 1 minus 1, 1. So that dot that becomes x minus 2y minus 3z. Minus 1 times 1 is minus 1. Minus 1 double minus is plus. So that becomes minus. So minus minus plus 1. So that becomes minus 2. And then you get minus 1 is minus 1. Minus 1 times minus 3 becomes plus 3 is equal to 0. So if we simplify, we get x minus 2y minus 3z is equal to 0. And that, ladies and gentlemen, is the answer. So here is the Cartesian answer. So note, the answer is typically of the form, note, answer is of the form ax plus by plus cz is equal to d, where a, b, c, and d are real numbers. Alright, so here a is 1, b is minus 2, c is minus 3, and d is 0. Alright, let's do another example. So here we have the points P, which is the point 203. We have the point Q, which is minus 401. And we have point R, which is minus 102. So the question is, does a unique plane exist containing P, Q, and R? Alright, so like before, we're going to start by calculating let n equal to P minus R cross Q minus R. So P minus R, that becomes the vector, first component 3, then it's 0, then it's 3 minus 2, which is 1, and then Q minus R, we do the maths, that is minus 3, 0, minus 1. However, note that 3, 0, 1, if you multiply it with a scalar minus 1, it becomes minus 3, 0, 1. So you can do the cross product, but you can also say by Theorem 1.7.4, so part 5, because the two vectors are scalar multiples of one another, we get that this works out to be the 0 vector. Alright, this works out to be the 0 vector. Alright, so what does this mean? This means that P minus R and Q minus R are scalar multiples of each other. This is bad news. Alright, so if you work out P minus R cross Q minus R and you get the answer is the 0 vector, that means that P minus R and Q minus R are scalar multiples of each other. In other words, they lie on the same line. In other words, a line exists that contains all 3 points. So our conclusion, no unique plane contains P, Q, and R. Alright, so in this case, what happened was, because P, Q, and R lie on the same line, it comes from the cross product calculation, so we know that there's not a unique plane containing P, Q, and R. Alright, so let's do one more example before we finish the video. So let P be the plane whose Cartesian equation is all of the 3D vectors x, y, z with a condition 3x minus y plus z is 3. So we want to find a vector equation for a plane. Alright, so you've got to be able to jump between the two. Go from a Cartesian equation to a vector equation, and from a vector equation to a Cartesian equation. So here we're given a Cartesian equation, and we want to go to a vector equation. Alright, so the first step is we need 3 points. So we need 3 points. So there are infinitely many points on the plane. Alright, so there are infinitely many points you can find on the plane. Alright, but I'm going to make my life easy, and I'm going to do the following. I'm going to take let x equal y equal to 0. So we get 0 minus 0 plus z is equal to 3. So z is equal to 3. So we can see that the point 0, 0, 3 is sitting on plane P. I'm going to give that point a name. Let that point be R. Alright. So you could have made x 20. You could have made y 30. Alright. And you could have solved for z and you would have found another point on the plane. But I just want to make sure I don't make a mistake with my calculation. So I'm making x 0, y 0. And then I solve. That means z must be 3. So I get the point 0, 0, 3. Now, I had so much success. So let x equal to z equal to 0. So we get that minus y is equal to 3. So we get y is equal to minus 3. So I'm going to give that point a name. So I'm going to call this point P. So P is x is 0, y is minus 3, z is 0. That is sitting on plane P. Alright, now I'm going to need another point. Remember, for a line, you need 2 different points. For a plane, you need 3 different points, not all lying on the same line. So now I'm going to make y equal to z equal to 0. So we end up getting the following. So if we plug it into our plane and we solve this, we get that 3x is equal to 3. So x is equal to 1. So now we get a point Q. The x value, which is 1, the y value, which is 0, and the z value is 0. That is also sitting on the plane P. Alright, so now we've got to make sure not all on a line. Alright, so if we found 3 points on the same line, we need to find more points. So we've got to verify that they are not all on the same line. Alright, so now I'm going to calculate P minus R cross Q minus R. So P minus R, so if you subtract those 2 vectors, do you agree with 0 minus 3, 3, minus 3 I mean? And if you do Q minus R, do you agree with 1, 0 minus 3? And if you do the cross product of these 2 vectors, I'm going to leave it for you to verify. I got 9 minus 3 minus 3. And this is not the 0 vector. Alright? So this is good news. This means we found 3 points on the plane, not all on the same line. Not all on the same line. If we were unlucky and we discovered 3 points on the plane on the same line, then we had to go and find a 4th point or a 5th point. Alright, so we need to find 3 points on the plane, not all on the same line. Alright, and so because we found 3 points not all on the same line, we can now say by Theorem 1.7.7 and vector equation for this plane is you take your rands to spar or checkers, where S and T are real numbers. Alright, and now you just fill in I need a little bit more space. R, remember R was the vector 0, 0, 3. S is just the parameter. P minus R we worked out is the vector 0, minus 3, minus 3. And Q minus R is the vector 1, 0, minus 3, where S and T, emphasize that, where S and T are real numbers. Alright, NB, answer is not unique. Alright, if you found 3 other points, P, Q, and R on this plane, your representation for the vector equation would look different. Alright, but there you go, ladies and gentlemen. I hope you enjoyed this video. Please come back for another video on chapter 1.7. Bye.